All right, let's talk the lesson for today. We're doing calculus, of course, and the thing about today's lesson is when you graduate college and you're like, you know what? I thought I was gonna do engineering, but I love math. I thought I was gonna, but calculus 4 was my favorite class I ever took. Do you think you're gonna go to your job and they're gonna give you a worksheet and say, I need you guys to take these derivatives? You know, that's not exactly how that works, right? They're not just gonna pay you to do derivatives. So of course, we've been talking about, okay, now can you actually use those derivatives? And can you find the maximums? And can you find the minimums? And can you find the concavity? And can you stationary points? Which is somewhat useful, for sure, right? You could draw, use your graphs and then try to find the maximums of those graphs and try to figure out, okay, well, that's important. But again, if you have a calculator, you can kind of just do that stuff with a calculator. In fact, most of the programs that they're going to be putting data into are probably going to tell you the maximums and minimums instantly without you doing anything. So again, we're learning these things, which is good, but I don't know that they're actually, but there are more difficult questions. And we're going to start that by talking about what we did before we started, okay? The measurement cut from the corners of this square. So the idea was everybody got this piece of paper, everybody cut out the square, and we all did that. First thing to pose to you, did everybody start with the same piece of paper? Yes. Yes, everybody started with the same resources, let's say, okay? Second, we wanted to make a box by cutting out of the corners and then folding up. We have a little bit of waste, those pieces that we cut out. Let's fold up our box and let's try to come up with the, what is the volume of our box? Did everybody get the same volume? No, of course not. So that's our first kind of interesting thought, is that even though we all start with the same and we all are doing the same thing, we are not all getting the same volume. Now, if we didn't all get the same volume, that means if we had different volumes, somebody's was higher than somebody else's and somebody's was lower than somebody else's. So you guys did this, right? Let's get your results. So how much did you cut out of the corner?
1 inch.
Okay. Cut 1 inch. And what was your volume?
33.0625 inches.
33.0625. I mean, sure, that's a lot of decimals. Maybe it'll come into play. How much did you cut, Josh?
3 inches.
3 inches. And what was your volume? 9.19. So a pretty drastically less amount of volume for sure. And what did you have?
I did 2 inches.
2 inches. Okay. And what was your volume?
I had 26.28.
All right. Okay, so there is definitely a variety. What you pick and how many inches you decide to cut is going to change your volume. And maybe we have different volumes that we're looking for. The one where we cut 3 inches out is going to really chop into our box. It's going to make our box a lot taller and skinnier, for sure. And maybe we want a box that's a little bit taller and skinnier, like a trash can, I heard you guys saying. But let's say I'm a company and I purchased 1 million square pieces of metal, and I was just gonna make 1 million boxes, and I wanted to sell them, and I wanted to make sure that when I made these 1 million boxes that I was getting the absolute biggest bang for my buck, and I wanted to make the absolute biggest box by volume. So who's getting the contract here?
Me.
You are. Now, let's say I had 1,000 calculus students do this same question. Alec, you're the winner in the room. Do you think you would win out of 1,000 calculus students? Probably not, because really, you just guessed. I mean, you just picked 1 inch. Okay, sure, and then I'll just do 1 inch and then no problem. So there is maybe a higher volume that we can make from this box. But how do we find it? Are we just supposed to just, here, you go try 4 inches, and hey, you try, 0.5, and you try 1.5, and you try 1.75, and you try 1.2, and then you try 1.3. I mean, that's going to be awful. So how can we actually figure this stuff out? Math. Calculus. Now, before we get into it, do you understand why this is a good skill to have? Why this is something that a company is always looking to do? I always think about when I was when I was a kid, every soda, every non-soda beverage was in a 12-ounce can. And they're still around, the 12-ounce cans, right? But now, there's all these little tall, skinny ones, right? We're seeing these tall, skinny cans. My wife drinks Celsius, and it comes in this little tall, skinny, whatever. That is not just an aesthetic choice, right? Some company has paid a mathematician to calculate, based on the aluminum price, based on how the aluminum is made, how can they make the most efficient can? Or maybe how can they stack those cans in the shipping truck? Or maybe how can they, right? So all of those decisions are mathematical decisions. I always think about like toilet paper rolls. You guys are maybe just a little bit too young to have shopped for toilet paper rolls. But if you go to shop for toilet paper rolls, I guess you've seen commercials and stuff, it'll say giant rolls. 1 giant roll equals 6 mega rolls. And then it'll say a mega roll has the value of 4 standard rolls. And it's all just ridiculous. But it's not because the company wants to have a cool mega roll. There's just a mathematician who said, if we just put twice as much paper on the same cardboard, we'll save money. So all of this is all mathematical. And how can we actually do some math to calculate this? Well, what are we trying to do? What is the problem that I've created here for you guys?
Find the most volume.
Find the most volume. And if we think about what we've been doing lately, which is looking at graphs, if we can graph the volume and then just look for when the volume is at its highest place. So our goal will be come up with a graph for the volume and then attack it wherever its maximum is. So, volume. We need to think about volume. We're talking about, luckily, a very easy shape. What is the volume of a box? So it's not a square, it's just a box. Length with height. God, I don't know how to make that squeakless. It's very annoying. But for our shape, we can make that even better, because for our shape,
So we can do L squared H.
sure, right? We cut the same length and height, or the same width and height. 2 of those letters are the same letters. So maybe we call it length squared height. I mean, those letters don't really matter. In fact, why don't we just get rid of those letters altogether? What can we replace those letters with? The letters we like in math, right? V equals something like x squared y. Okay? Okay. If we can take a derivative, then we can maybe look for where is that derivative at its maximum. So that would be when the derivative is equal to 0, we could look for the height of this. So we have these for volume. We have x's. We have y's. So the derivative, product rule. So we have 3 different variables here, which is a lot going on. When we go to take the derivative, typically we have something like f of x, and then we take the derivative. Or sometimes we have y, and we say like dy dx. So one thing we can do is we can say like dv dx. That's like our derivative of the volume. Set it up like that. Now, even if we do this, I'm a little worried that we're still going to have like a whole bunch of letters here. The derivative of x, you know, we're going to, maybe we get 2xy plus x squared, and the y can just be 1. But we've never done questions like this either, where we're taking derivatives of multiple letters, and that has its own rules that we haven't really learned yet. That's called implicit differentiation. So I don't know that this is going to work. Maybe we can use a different kind of formula to try to use substitution and replace one of our y's with our x's. What is x and what is y? So this here, let me change to black. This is our x, right? And then whatever this would be is our y value, right? So this kind of ends up being our height, and this actually, if this is our box, the way we have it written, this ends up being like the height of the box, and this, so it's actually backwards. Let's just go for the eraser. It's actually backwards. This is the y because this is the x by the x. Okay, so you're good.
I was just gonna say we can like find the length and then do minus 2y. So x equals the full length minus 2y.
Exactly. I like how we're thinking, because we can't do this derivatives with multiple letters. So instead, how can we talk about y using x's? So I like how you're thinking, right? Let's reframe that, or let's rephrase that y. What is the full length of our box that goes all the way across? Did you guys find it?
7 3/4.
I've got one here.
It was 7 3/4 because when I subtract 1 inch.
7 3/4.
5 3/4.
All right, measuring carefully. Just about, not quite 7 3/4. For our box, it looks like it's 7 1/2. I think it's supposed to be 8, but maybe the printer scaled it. I don't know. Let's go for 7 3/4. So what's that, 7.75 we can go with? Yeah. Okay, so we got 7.75. That's the full length. And 7.75 is x plus 2y. One of the x's and 2 of the y's. And so let's then solve for either x or y. And once we solve for either x or y, then we can substitute it into that volume formula, and it'll be all x's or it'll be all y's. You want to go for the x's or for the y's? I think it's smarter to go for the y just because we're more comfortable with the x's. Okay, cool. So let's solve for the y's. Subtract the x, divide by 2. And so I'm getting that y is equal to 7.75 minus x over 2. We cool with that?
Yes.
Okay, let's go over here. Substitute everything in. V equals x squared. And then all this mess. 7.75 minus x over 2. Our goal is to handle this, try to take a derivative of it, so let's make this look a little bit nicer. Maybe we'll just distribute this and sort out this fraction a little bit better. So 7.75 divided by 2 x squared minus x cubed divided by 2, or 1/2, or whichever, and 7.75 divided by 2, let's just leave it like that, because I'm noticing that I have that x squared, and when I take that derivative, it's going to go ahead and get rid of that too. So at this point, I'm thinking about my volume in terms of all x's. And if I take my derivative of this volume, I can write it like dv dx instead of dy dx. And this represents the change in volume. And when I take the derivative using power rule, 7.75x, subtract 1 is just an x, bring that 3 out front, minus 3/2 x squared. I think that's a decent derivative. That would be whether our volume is going up or our volume is going down. And what we're looking for is when that volume is 0. That way we can pinpoint whether it's a maximum or a minimum. Equals 0. So how can we solve this equal to 0 now? What's up? Yeah, normal algebra to solve when it's equal to 0. So what's...
Oh, you're asking still like steps.
Right. What?
So just first take out an x.
Right, GCF. Okay, cool. Then we're in good shape. 7.75 minus 3/2 x equals 0. So we can already see one of our answers is going to be x equals 0. The other answer is going to be 7.75 equals 3/2 x. We multiply by 2 on the other side. So that would be not all that bad. 15.5, right? 15.5 equals x. And then, or 3x, sorry. And then divide by 3. And if we divide by 3, we're going to get 5.5 which is, all right, let's go back and let's make 15.5 into a fraction. Then we can be extra sure. 15.5 would be 31/2. Then we can divide by 3 and we'll get 31/6. Okay, so we have just determined what happened to us here. So I'm thinking, first of all, what if x is 0?
There's no height.
We just basically cut corners that, oh, don't do that. We basically cut corners that chopped the box and we wasted the whole thing. Is that the maximum of the volume? It's the minimum of the volume, because that's when there's 0. There's not even smaller than Josh's box somehow, right? So we know that 0 is the minimum, and that makes a lot of sense, right? We cut the whole box away, there's nothing left. X equals 31/6, which is pretty ugly. That's the other one, and I suppose that is the maximum. Now, 31/6, what is that? Is that how much we're cutting out of the? That's what's left. So this should have a length of 31/6, which is 5 1/6, which is 5.13 or something like that. I don't know. So now, how can we figure out the volume of our whole box, right? Because this would be what the maximum volume is, right? That calculus student who wandered in, who happened to have the biggest volume, who's getting the big paycheck at the end of the day, maybe it's bigger than Alex, or maybe it's going to be surprisingly close to Alex. 31/6 is the side of the triangle there, or the side of the square in the middle there. And if we think about, I guess we need to get a decimal. What is 31 divided by 6? Who's got the calculator? 5.16. Oh, okay, I was relatively close. All right. 5.16 repeating. So we need to figure out what are these y values. So the whole thing is 7.75 across. And the middle part needs to be 5.166 repeating. And when we do that math, what do we get? What? 2. Are we all charging? Is that our problem? 2.584 repeating, I'm guessing. Okay. Is that the amount that we need to cut out of our corners?
Well, from each side, right?
So this whole piece, we got to divide that by 2. All right, and when we divide that by 2, 2.584444 divided by 2 is 1.29222 repeating. All right, so that is our maximum amount of our maximum volume amount that we need to cut out. Now, if we sat here all day and we just said, here, I'll do 1.1, 1.2, 1.3, 1.4, 1.5, you do 2.2, 2.3, whatever. We still wouldn't have gotten exactly to that, maybe ever. And there always would have been that little bit extra. So doing it mathematically is pretty much the only way we likely would have found the pure maximum value. Now, in order to take this, remember this is how much we want to cut. This is our y value. And this is our x value. Our volume should be length times width times height, which is x times y, 5.166666 times 5.166666 times 1.2922222. And the volume that we got from our perfect triangle, why do I keep saying triangle? Box. Boom, we get a whole extra square inch plus, and it's really a cubic inch because it's volume, but you pretty much get the idea. We're getting a whole extra bit there. Now, if I was working for Coca-Cola and I was gonna make 1 billion cans of something, that 1 inch, 1.5 inch cubed is like invaluable, right? It's so important. And so this is called optimization. Okay, optimization is about looking at something that could be real life measurements, trying to come up with a little equation that you can then take the derivative of, set equal to 0, and solve. And when you find those stationary points, they might be maximums, they might be minimums, but they're important one way or the other. And luckily, it's also pretty obvious whether it is a maximum or a minimum, because 0, right? Your volume is 0. I don't know if that's the big, it's clearly the smallest. So this is a little bit of real world optimization, and obviously it's important and useful, and people will pay you to do it. Let's see some optimization questions. Okay, so right away, goodness, there's a lot of, I don't know what this is, mess on the printer screen, I guess, whatever, but for whatever reason, the problems didn't have any work for this, or any space for the students to do work, which you definitely need on this kind of stuff, and I just had to do some cutting and pasting, which is why it looks like a mess. But the following diagram shows the graph of the function f of x equals 2 sine x plus 2 from 0 to 2 pi. Okay? A vertical line segment is drawn between the horizontal line y equals 5 and the curve f of x, where a on y equals 5 and p on xy on the curve are shown. Okay, so basically it's just a line that goes straight up and down between the curve. And it can go left and right. Okay. Explain why the length L of AP is given by L equals 3 minus 2 sine x. So we want to think about this and try to just put useful information on the paper and then try to combine things together in a way that makes any sense. So for this question, A, maybe it's not jumping off the page at you where this 3 minus 2 sine x is coming from, but basically just what information have they given you for this question?
They give you the f of x formula.
They gave us the f of x. F of x equals 2 sine x plus 2. Great. What else did they give us?
The line y equals 5.
The line y equals 5. Now that's more or less it. They gave us the boundaries from 0 to 2 pi, but that's not really mattering for us too much. All the other numbers are basically the 5s and stuff. And how do we get from this 5 and 2 sine x plus 2 all the way to 3 minus 2 sine x? So I'm definitely noticing that I'm seeing 2 sine x and 2 sine x. Those are matches. So where is the 3 coming from? The 5 and the 2. Right, so this is basically we're trying to figure out the distance here, which is going to be start at 5 and subtract away whatever your curve value is. And so L is going to be start at 5 and subtract away your function. Now make sure when we subtract it, we kind of do that distribute. And that, of course, is why L equals 5 minus 2 is 3 minus 2 sine x. All right. Now, find the minimum and maximum length L by using differentiation on L. So they're just kind of walking us through for this question. So we want to go ahead and take the derivative. Now, again, kind of the best way to write this is dl dx, because it's like we're taking the derivative of L based on x. Okay, sounds good. The derivative of 3, who cares? It's going away. The derivative of negative 2 sine x is going to be negative 2 cosine x. And we want to find when is this equal to 0. Negative 2 cosine x equals 0. We can divide both sides by negative 2. It's just we need to figure out when is cosine x equal to 0. And cosine x is a graph that looks like this. It is 0 at these two places, pi halves and 3 pi halves. So it is 0 at x equals pi halves and x equals 3 pi halves. Now, we did a little bit of math, we did a little bit of calculus, we did a little bit of derivatives. We set it equal to 0. Those are stationary points. They're extrema. They might be maximums or minimums. For this question, it's not as blatantly obvious whether it is a maximum or a minimum just by looking at the numbers. But if we go back up here to our graph, looks like I moved this on accident a little bit. If pi is 3.14, which is about right there, well then this is about half of a pi, and this is about 3/2 of a pi. You can see that here is our maximum, and here is our minimum. Now, if we needed to prove that, you can't really just say look at the graph, right? So if we really needed to prove this, if we needed to do a bit more, we could take these x values and we could plug them in to the original function that we found for L, and we could see what happens, what comes back. So we could do something like L of pi halves is, plugging it in, I guess it's 3 minus 2 sine of pi halves. Sine is a function that looks like this. Pi halves is 1. And so this would be 3 minus 2 times 1. And so this would be 1. We could try the other one as well. L of 3 pi halves, which would be 3 minus 2 sine of 3 pi halves. And that 3 pi halves sine is -1. 3 minus 2 times -1, which is going to be plus 2, which is going to be 5. So these are the lengths of L. The smallest that it could possibly be is 1. And again, visually, that makes a lot of sense. Right here, that's the longest that, or the shortest that L would be, this distance, and we can read on the picture that it looks like 1. And right here, that is the longest that L could be, and it has a length of 5. So this question, they give you the picture already. They try to make it a little funky because they have the signs and the lines, but let's go and check out the next one. A point on the line y equals x has coordinates of x, comma, 2x. Let a equals 5.0. Determine or express the distance between P and A in terms of x. So this one is not nearly as obvious. Okay, I know that we're looking for some sort of point here that is probably going to have to be either closest or farthest from A. It doesn't make any sense to find when it's farthest, because it could just be a billion and it could have, be a mile away. So we're probably going to be looking for how close can we get, and I can't really tell just from looking at the picture. So this is our important part of today. This is really what you're trying to learn, is how can you come up with that very first equation? Because once you do that, you just take the derivative, set equals 0, okay, whatever. Like he was saying, it was just algebra. So how can we set up with A? If we can find A, we're probably going to be getting this question right. Express the distance D between P and A in terms of x. So, distance formula. Do we know the distance formula? D equals square root, parentheses squared, plus squared, minus is in there. It's got to be x minus x, y minus y. Now, we want to make this specific for our question, and so we have 5, 0, and we have x and 2x. So let's kind of make this look a little bit nicer. Okay, so this would be, let's do the first one. 5 and 0 minus, minus, and this one would be x and 2x. Okay, so we've done it. We've established our distance formula. Now, I will say that they did help us out a lot here with this x and 2x part. If they had left that out and they had just said, here's the line y equals 2x, it would have been probably pretty tough for us to make the connection that we could write the y coordinate in terms of x. Because again, we have to get only one variable, because we only really know how to work with derivatives of one variable. So now that we're here, B, find derivative of D with respect to X. Honestly, I don't really know that we're ready to do that yet. Okay, this is a mess, and that probably could be made a whole lot nicer. Okay, I'm noticing that this part can definitely be made a whole lot nicer. I'm noticing that this part could probably be FOILed and then combined with that other part. So before we do the derivative, let's make this look a little bit nicer. The distance is equal to the square root of, I'm going to FOIL this, 25, that would be -5, -5, -10x, that would be -x, positive x squared. Over here, that's -2x squared, that's positive 4x squared. Okay, let me write this a little bit nicer. I'm probably going to swing my x squareds to the front. 5x squared minus 10x plus 25. That looks much nicer. That definitely, I think we're ready to take the derivative here. I'm noticing maybe we could do a GCF of 5, but I'm not really seeing how that's going to make things much easier. Then we're just going to have parentheses inside of a square root, which I think this is probably about as good as it needs to be. The derivative of the distance in respect to x is equal to chain rule, a funky thing inside of a square root. When we do the derivative of a square root, it's 1 over 2 square root, whatever it used to be, 5x squared minus 10x plus 25. The top would be where the chain rule shows up, where we took the derivative of that inside, which was 10x minus 10. And I am noticing that we could do a little GCF because I see 10, 10, 2. Those are all factorable by 2, so maybe we do that already just to make things smaller and nicer. Okay, I think that's nice. I think it's a beautiful little derivative. We've done A, we've done B. Hints, find the minimum distance D and the coordinates of the corresponding point P. All right, so now that we've done this, we found the derivative, we basically have always the goal of derivative equal to 0. So let's take this, 0 equals 5x minus 5 over square root of 5x squared minus 10x plus 25. And of course, when we're trying to set this equal to 0, does the bottom even really matter? Not really. We're going to multiply that bottom over to the other side. It's just going to evaporate. And so what are we getting for our x value? 1. I agree with you. 1. All right, if that is our x value, let's complete this question. Okay? The question has asked us, find the minimum distance and the coordinates. All we have is x equals 1. What is that x equals 1?
Where the distance is the minimum.
It's the x value of the minimum distance, all right? So minimum at 1 something, what would the y value be?
2.
2. Because it's y equals 2x. And so it's just doubled. Now, the last thing is, what is the actual distance? We can go back and plug it in. And we could use the full distance formula with the y and the x, or we could use our fancy distance formula that only uses x. It doesn't really matter. We have this one that only uses, I think that one is probably good enough. To go back here, put in a 1 to this x and a 1 to that x. That's going to be 5 minus 10 plus 25, which is going to be 30 minus 10, which is going to be 20, which is going to be square root of 20, or I guess 2 square root 5. So, optimization. The main thing, and we haven't really had to do it yet, is make sure that you can get one variable thing and then take that derivative and then set that derivative equal to 0. The derivative normally isn't that bad. The setting equal to 0 is something that we should be able to handle with, you know, one of the many skills that we have there. It's the setup that is most of the difficulty, which we haven't really had to do yet. Again, I think this is, you know, worth pointing out that the distance being the square root of 20 is just a distance that you wouldn't really be able to find otherwise, right? It would take a ton of work to try to figure out what that distance was if you weren't using this optimization. Okay, here's a question that finally isn't doing that first step for us. So this is hugely important that we look at this one. A rectangle has sides x and y, and its perimeter is 40. That's all we know. Express y in terms of x. So we need to somehow set up an equation here where we can have y equals something something x. Now obviously we know that the perimeter is 40. That's really the only bit of information that they've told us to help us out. So we definitely need to use that information. How can we set up an equation using that with y and with x? 2x plus 2y equals 40. Excellent, right? Because really that's perimeter equals 2x plus 2y, and then we put the 40 there. And it says express y in terms of x, so let's solve for that y. Subtract the 2y to the other side, or maybe subtract the 2x to the other side and divide. Doesn't make a difference. I'm going with y equals. I subtracted the 2, made it 40 minus 2x, and then I divided by 2. As you can see, all these numbers divide by 2, so we can just kind of get rid of those. 20 minus x. Or negative x plus 20 if you did it the other way, but this way looks nicer. Sweet. That's a 1 marker, and that's definitely a pretty easy setup. B. Hint. Express the area of the rectangle in terms of x. Okay, so why are we incorporating the area here? Well, if we don't incorporate the area, what are we really supposed to be doing? Are we supposed to find when x is maximum? I mean, who cares? That's just when you have a really long side. But now that we're incorporating area into this question, we're going to have something to be able to kind of do some calculus on. Area equals xy. Let's get rid of one of those letters. Let's get rid of the y, because we have this little conversion here. So let's do a swap out. Area equals x times 20 minus x. That's another little 1-pointer. And now, let's take the derivative to find the maximum area of the rectangle. Very similar to our box question. The derivative of the area by x this could be 20x minus x squared, which would be 20 minus 2x. Set that equal to 0. Add the 2x, divide by 2, x equals 10. And so when x equals 10, that should be our maximum area of the rectangle. It does say justify your answer. Now this wasn't really all that much work for C. How can we get those extra marks by justifying that this 10 is a maximum? I think the easiest way to justify maximums and minimums is the second derivative, because it's normally easy to find the second derivative and you normally don't have very much left. We know that concave down makes maximums, concave up makes minimums. So if I think about the second derivative of the area, d squared a dx squared, which would just be -2, that's the only thing. Well, that means that it's never changing, and the second derivative is always concave down, which means we have a max. All right. So make sure we finish C. Use the derivative of the area to find the maximum area of the rectangle. I don't think we did that yet. I think we found the nice x value. If the perimeter is 40, I got to give me one of those certificates. All right. I went ahead and I found the y value. Then I said area is 10 times 10. Okay, the area is 100. Are we feeling good about that? Okay, D says find the minimum value of A. What do we think the minimum value of A is? The minimum area that you could create?
I said it's less than 2.
I don't think I can go with it does not exist.
There's no absolute minimum.
Just like
There's no minimum number?
Because you can just infinitely keep going, right?
You can just infinitely keep going? What does that mean? Like, can you go smaller than 10? Can you go smaller than 5? Right? Can you go, I mean, maybe, can you go smaller than 1? Sure. I disagree that you can go infinitely smaller because eventually you're just going to hit 0.
Oh, okay. So, because that's right.
You can't have the negative area of a box. So the way that I could find the minimum value of a, because when we did the first derivative, it only gave us 1 value. And that's because, you know, our graph looks something like that. And like he's saying, it does go down forever. And this is our nice maximum at 10, 10. But these values are as small as it could get. We can probably predict where those values are as well. Now, my graph has it over here in the negatives. When it comes to optimization, negatives, if we're talking about sizes of things and lengths of things, negatives aren't really working. So I don't really like that I drew this, or I randomly sketched this over here in the negatives, because you're not going to have a negative length of x or whatever. Were they listening into us this whole time? So one thing I could do is I could just set the area that we found. This area equals 20x minus x squared equal to 0. And see x 20 minus x. And when is that equal to 0? At x equals 0 and at x equals 20. And that is making sense, because if my x value is 0, then I don't have a box because I don't have any area at all. And if my x value is 20, then I've used 20 out of 40 and 20 out of 40. How much is left for the y? 0. And so it's 0 again. So I could also consider that original function equal to 0 to find that. Okay. Look at this last one, because I tried to give you one that was less and less intuitive each question we went, and we got to this one. Now again, this is definitely a valuable question that a company or some sort of researcher or something would want to figure out. How much of a box can we fit under a curve? I saw some IAs for IB where a kid was trying to come up with a curve that he could fit like a banana under the curve, because he was trying to find the perfect curve to make a box for the banana that he brought to school every day, kind of thing. And so he was using these curves that looked like this and they looked like this, and he was trying to make sure that he could fit his, I don't know. Anyways, this kind of thing, area under a curve, is a huge topic in calculus, but this is a little bit different because this is trying to figure out a box value under here. Now, it's kind of like ours in that we could make a box that looked like that, or a box that looked like that. And which one of these boxes has the biggest volume? So it's very similar to our question, except for ours is a lot more physical than this is a little bit. So let f of x equal 80 minus x power 4. Again, anything they give you in the question, we're going to be wanting to latch on to and thinking about and using. Rectangle ABCD is inscribed in the region of the curve. F of x as the x-axis shown in the diagram below. Assume that he lowers, I think that it's supposed to be the, assume that the lower vertices of the rectangle have the coordinates negative a0 and a0. So obviously it needs to be symmetrical. So they just went ahead and called this a, and or I guess this would be negative a, and this would be positive a. The first piece here is trying to walk us through that first step. Show that the area of the rectangle is given by S equals, and I think they're using S because we already have A's in the question and they don't want to confuse us with those A's, I suppose. All right. When I'm thinking about this, I have my rectangle here. And I want to think about only half of it because I know it's doubled and it's probably a little bit confusing for me to think about it being doubled. So let's just stay here. This rectangle, what is the length of the bottom piece? A. And what is the length of the top piece? Now this one's more complicated, of course, because it depends on where you go based on that function. So this is going to be the length determined by the function 80 minus a power 4. That's what it was, right? Yeah. So picking the bottom is going to be super obvious. You can just pick 1 or 2 or 3. But picking the top vertices, you have to then take that number and plug it into the formula or into the function. And so that's why this looks so complicated. Now, how do we show that the area is equal to all of that?
Multiply all that by 2.
Right, so we need to take the length times the width and double it, just like you said. So S should be 2 times the length times the width. Which is going to be 160a minus 2a power 5. And that's exactly what they had. So perfect. That wasn't too bad. Nice job, Josh. Find the maximum value S, justifying that it is a maximum. So one thing that I've noticed, I taught this last year in the regular calculus class, and kids would get all the way to the end of the question, and they never took a derivative. And it would just be like, dude, you're in calculus class, and you never took a derivative. Like, you know, you have to take a derivative at some point. So once you set it up and you have only one variable, let it rip. Like, let's take a derivative. The derivative of S with respect to A. Notice that we're keeping our variables looking nice and sharp here. We're not using X's, we're using A's for this question, I guess. That would be 160 minus 10a power 4. I'm starting to see why this question is so nice. Set that equal to 0 because we're looking for maximums and minimums. And solving, I think this is actually going to be kind of nice. 10 equals a power 4, add to the other side, divide by 10, 16 equals a power 4. Do the 4th root of 16, which is going to be plus or minus 2 equals a. All right. Importantly, we get that plus or minus 2, which is our 2 options. And when we look at that, that's because, you know, A could be over here in this position, or it could be over here in this position. Okay, that makes sense why we got those 2 answers. It does say justifying that is a maximum. So we still never found the maximum value of S. So let's go ahead and take that A, which is 2, and plug that into the S value. S of 2 is equal to 2 times 2 times 80 minus 2 to the power of 4. S of 2 is equal to 80 minus 16 is 64. 64 times 2 is 128 and 256. So our biggest area is 256. And how do we want to justify that this is a maximum? I think second derivative is you know, more or less definitely a good place that I'd like to go. So that would be negative 40a cubed. Is that the second derivative? 160 just becomes 0. 40, I think that looks good. I can plug in my 2 here, negative 40 times 2 cubed. And honestly, who even really cares what that number is exactly? It's gonna be a negative number for sure. So this is a negative number, which means it's concave down, which means we have that maximum there. Okay. Optimization. The main step is this first step. If you're finding yourself like, I don't even know how to start this question, write everything down. Look for how can I make an area or a surface area or a volume equation that only has one variable. A lot of times we saw a question that looked like this, which I've now written all over. But the start of this question was use perimeter, use area, and then make a mega equation. That is a super popular thing. Okay, on your homework, I think you have 2 or 3 questions like that, where you look at volume, you look at surface area, and then you combine them together. All right, optimization day 1.